Up till now, we have studied about one type of organosilicon compounds, that is trialkyl silyl halides, and now we shall study the second type of organosilicon compounds, which is the silyl enol ethers. Now, Silyl enol ethers have a very pertinent method for synthesis, that is known as Brooks synthesis or Brooks rearrangement. It is known as Brooks rearrangement because it was discovered by a Canadian chemist, Adrian Gibbs Brooke, in 1958. It is also known as 1,2 Brooke rearrangement or 1,2 Silyl migration. This reaction is characterized by being an intramolecular rearrangement reaction. So, the 1,2 migration of a silyl group from carbon to oxygen in basic conditions is known as Brooke rearrangement. It is a very important rearrangement reaction, which is also used as a method of synthesis for silyl enol ethers. So it is a rearrangement of alpha silyl oxyanion to alpha silyl carbanion involving a penta-coordinate silicon intermediate. Via this intermediate, the reaction proceeds. So as you can see that Brooks rearrangement is accomplished in 3 steps. Step 1 involves the removal of a proton, that is also known as a proton abstraction, from the hydroxyl group in the presence of a base forming an alkoxide ion. This ion then starts acting as a nucleophile. So that is in the first step of the reaction that you can clearly see. Now step 1, I have in the side box, right side of the reaction page, I have written BDE, that is the bond dissociation energy. So bond dissociation energy of OH bond is the value that is mentioned there. Now comes step 2. So step 2 involves the migration of silicon carbon to silicon oxygen bond, and this occurs through a pentavalent or pentacoordinate, as I had also said earlier, pentacoordinate silicon transition state, and has a partial charge on it. Now this the intermediate that I have written on the top of the arrow, this is a cyclic 3-membered transition state where silicon has a trigonal bipyramidal geometry. So for step 2, you can see BDE, that is bond dissociation energy for silicon carbon bond is given, and BFE, that is bond formation energy for silicon oxygen bond is also given. Now we come to step 3. So step 3 is easily self-explanatory, and thereby in step 3 you can see how silyl enol ether is formed with bond formation energy of carbon hydrogen bond that is given. What is the purpose of showing these energies, values of energies? Actually, in total, if you see, the bond dissociation energy comes to 878 kilojoules per mole, and bond formation energy comes to 1147 kilojoules per mole. So bond formation energy comes to be more than bond dissociation energy. Thereby, the reaction is favored by the formation of ether. Also, the rate of reaction depends on the amount of the added base, but this was not consumed and was used in stoichiometric amounts. So the reaction follows a false first order kinetics.